Now, one of the questions you might have, I would if I were in your shoes, and that would be, what grade am I getting right now at this point? Well, first of all, each and every one of you can still get an A because tests, the lowest tests are dropped. One of the lowest tests are the final. Well, for most of you, like all of you, did good. And therefore, if you're getting 90 and above on the test number 1, you're getting an A in my class. 80 to 89, you're getting a B. And lo and behold, nobody got lower than that. Boy, you guys are really, whatever you're doing, don't stop. Remember, whatever you're doing, don't stop. And now you know why I call them practice problems. All right, any questions about test number 1? Going once, twice. Okay, quick thing. Yesterday, I uploaded lab scores for labs you handed in, the first 2, and that's in Blackboard, so you can see it. Most of you did pretty good. For a few of you who haven't been handing in labs, get them in. They're easy points. You lose 11 points, that could be the difference between an A and a B, or B and a C. So get your labs in. Now, if you're having a problem with Labster, let me know. I know 1 or 2 of you are. See me after class today. The one person hopefully she's here, he's here. Or come to my office hour. Don't forget, my office hours are tonight and Wednesday night, 6 to 7. And let's move on. All right, time for my thumbs up, people. Can you all see single bond on the screen? Thank you, thumbs up, people. I love you. I love all my students. All right, last week I was talking about single bond. When we talk about covalent bonds, when you share 1 pair of electrons between 2 atoms, a double bond is when you share 2 pairs of electrons between 2 atoms. And a triple bond is when you share 3 pair of electrons between 2 atoms. And we did Lewis structures of the following molecules. I don't think I did carbon dioxide. Let me ask, did I do carbon dioxide? I don't think so. Let's do it. I'll do it. One thing I've been amiss at, and I'll do it later today, is send out a list for what videos from my Chem 1105 class that you should be looking at along with my lectures here, my mini lectures, to help you out. All right, let's look at the Lewis structure for carbon dioxide. Making room on my desk for my tablet. All right, carbon dioxide, CO2. Carbon, 4 valence electrons. Oxygen, 6 valence electrons. How do you know this? You look at the top of the periodic table and you see the number on there, Roman numeral or numeric, and that's how you do it. Now, carbon
We can't see what you're doing.
Oh no, I keep on doing it. Thank you. One of these days I'll remember I have to go like this. All right, everybody see it now? Let me check my thumbs up, people. Everybody see it? Okay, thank you. And whoever said I couldn't see it, thank you. All right, now oxygen. That's a sad looking oxygen. But anyways, oxygen has hold on, that is disgusting. That's better. Has 6 valence electrons. Now, if there are 2 oxygen, which there are, oxygen says to carbon, one of them, I have 2 single electrons. You have 2 single electrons. Let's form 2 pairs. And they do. And the second oxygen says, you still have 2 unpaired electrons, and I have 2 unpaired electrons. And let's share. And they do. Now, what kind of bond? Hold on one second. I do something to help me out. What kind of bond is between carbon and oxygen? There are actually 2 of them. I'll give you 8.2 seconds to figure it out. Actually, I'm going to drink some tea. And the answer is a double bond. How do you know? There's 2 pair of electrons. And so carbon dioxide has not 1, but 2 double bonds. Now, the next time you're with some friends, neighbors, or loved ones, and you see them exhaling, or if you happen to be with friends, neighbors, and loved ones, and hopefully someday we'll be out of social distancing and whatever. But anyways, and you see someone or you're drinking some pop, some beer, or carbonated wine, sparkling wine it's called, or champagne, the little bubbles in there are carbon dioxide, CO2. And that has 2 double bonds in it. So next time you see someone doing that, also when you burp, which I'm not going to do, but if you do, the gas coming out of your mouth, most of that is carbon dioxide. So when you burp, you can go, "Ooh, excuse me, I just let loose some double bond." No, don't. And that's how you do this. All right, let me just go through one more. I think I did this, but I'm just going to do the wrong thing again. Let me do the right thing. Let's do one more. I think I did this, but let's do a different one. Hold on. This is sodium cyanide. It's a solid at room temperature. Draw the Lewis structure. Now, whenever you see an alkali metal or an alkaline earth metal, they are never, ever in a covalent bond. They always form an ion. And we've done sodium, and sodium forms a plus ion. Just quick check with my thumbs up, people. I'm going to have signs made up for you people. Everybody sees sodium cation? Thank you, thumbs up, people. All right, now, what we do have left is carbon and nitrogen. Carbon has 4 valence electrons, nitrogen 5 valence electrons. And on a test, if I were to ask you 3 points each, say draw like I did with water and carbon dioxide, draw the Lewis structure for sodium cyanide, what would you do? Well, first of all, this has lost its 1 valence electron. That's why it has a positive charge and no dots. Now, carbon has 4 valence electrons. Nitrogen has 5 valence electrons. Notice nitrogen has 3 unpaired and carbon has 3 unpaired. And nitrogen can say to carbon, let's share our unpaired electrons. This has 3. This has 3. And they do. The non-bonding electrons pair on nitrogen are still there, and carbon still has 1 valence electron. Now, all atoms other than hydrogen, when they're in a covalent bond, want to have 8 valence electrons. If we look at nitrogen, it has these 6 plus this 2, and that's 8. Ooh, everything looks good. Now, carbon should have its octet, 8, and it's got these 6. Plus 1 is 7. That's not an octet, but where did this electron, remember, sodium has 1 valence electron, but it lost it. Where did it go? It went to the carbon. And now carbon has 8 valence electrons, but it has an extra electron, so it has a negative charge, and this is how you draw the Lewis structure for sodium cyanide. Remember, listen carefully. All alkali metals form cations plus 1. Sodium, lithium, and potassium, always. You show me an exception to that, and we'll be rich beyond my wildest dreams. And that's because it doesn't exist. If it does, let me know, and we will be rich. It doesn't. All right, now, how do you know that water, or better yet, what is the reason water has 2 hydrogens? What's the reason other covalent molecules have the atoms they have? And that's because you can determine the number of covalent bonds that at least 1 vacancy in an atom's valence electron shell to be able to form a single bond. In other words, you have extra, don't have a full octet yet. And if you have 2 vacancies, you can form a double bond, and 3 vacancies. In other words, you need 3 more electrons to get an octet. You can form a triple bond. This I won't ever ask on a test, and you'll see where this is going. So, carbon has 4, nitrogen 5, 6 valence electrons, and therefore 8 minus 4, 4 valence vacancies. Nitrogen 3, oxygen 2. What I don't have on there, the halogens, which are important, have 1 vacancy, and hydrogen, remember, its octet is really 2, has 1 valence, so it has 1 vacancy. And what does that mean? There are exceptions to that rule. Let's skip this because I'm never going to cover that on a test. And I've done Lewis structures for stuff like this. We did NaOH. All right. One of the things that you should know how to do I think I spelled simplest wrong. Did I tell you I'm always the first one down in spelling bee? Was in grade school. So question is, what's the formula for a molecule made up of carbon and hydrogen? Now, carbon has 4 valence electrons and hydrogen has 1 valence electron. Carbon wants to get an octet. Can you guys see me? Hold on. Someone beat me to it. Anyways, let me just check with my thumbs up, people. Nobody's yelled at me yet, but you see everything? Yep. Thank you, thumbs up, people. All right. So if we look at this way, how many hydrogens would you need to give carbon an octet? 8. Well, it's got 4. It needs 4 more. Each hydrogen has only 1 valence electron. So for every 1 carbon, you need 4 hydrogens. And this is the answer you would get. And therefore, let's take a look at this molecule, CH4. There's a name for it. It's called methane, but you know it as natural gas. And if you cook with gas in your house, if you have a furnace, which most of us do in Northern Illinois, I think everybody that uses natural gas to make heat to warm you in the winter, and if you have a hot water heater in your house, condo, or apartment building that uses natural gas to make the hot water that you used for your shower this morning or bath or last night or whenever, you're using methane CH4. You try this one. What's the simplest molecule, formula molecule formed by hydrogen and oxygen? Go. Oh, somebody's broadcasting the answer. That was good. All right, I think everybody's done. Let me move here. We have 1 hydrogen, 1 valence electron. We have hydrogen, I should say. We have oxygen with 6 valence electrons. It wants to have 8. So how many hydrogens do you need to get 2 more valence electrons? The answer is 2. And that's why water is H2O. And that gives everybody an octet. Remember, hydrogen's octet is just 2, so it just needs one more. Oh, let's do one more. These are fun. What would be the simplest molecule formed from nitrogen and hydrogen? I'll help you out. Nitrogen, 5 valence electrons. This is 1. Go. I'll give you 5.2 seconds. 5.1, 5.15, 5.2. Time's up. And I see people broadcasting the answer. Let's see if you did it right. And a lot of you did it right. So, but let me do it now. All right. Nitrogen has 5 valence electrons. It wants an octet, 8. How does it get 3 more valence electrons? Well, if each hydrogen could give 1, then you need 3 hydrogens, which is ammonia, which we talked about in class. Now, things get a little tricky when you have a double bond involved or 2 double bonds. But if I were to ask on a test, any of the examples I'd ask you would only be single bonds, covalent, 1 pair of shared electrons. And that's how you do that. Now, click. I've just turned off the switch. Will this be on a test? I just want to cover this briefly. Now, molecules have shapes. They exist in 3 dimensions, just like your hand has a shape, or the pen you're using, or pencil, if you're taking notes. And Lewis structures help tell you don't tell you the shape of molecules they exist in, and the shape is determined by valence electrons and the type of bonds. Remember, switches off. And this is determined by what's called the Vesper Theory, which is valence shell electron pair repulsion. And that is pairs of electrons, including non-bonding pairs, want to be as far apart from each other as possible. And that determines the structure of a molecule. And turns out that affects many things. If you have 2 pairs, it's linear. 3 pairs, remember, switches off. Trigonal planar, 4 pairs, depending, no bonding, tetrahedral, 1 bonding, trigonal planar, and 2 non-bonding is angular. And let's do something real quick. Time again for my thumbs up, people. Do you see shapes on there? Thank you. All right, and this shows you if it's 2 double bonds, it would be linear carbon dioxide. Methane is tetrahedral, And remember, this is the non-bonding electrons. E stands for empty, I guess. And ammonia is trigonal planar, water is bent. And the only thing I just wanted to show you was that it turns out that molecules have shapes due to their pairs of electrons in covalent bonds. Now, this won't be on a test, but it's good to know, switch to law, that not all atoms are equal. And some of them are stronger than others when it comes to keeping electrons near each other. And so when you have two atoms sharing electrons, one might be stronger than the other, and it says, I'm bigger than you, stronger. I'm going to keep the electrons closer to me. And when you look at the periodic table, when you move from left to right, bottom to top, we call this strength electronegativity or electronegative. Atoms have more electronegativity. And when you go from left to right, it's more electronegative when you go bottom to top. So the most electronegative non-inert gas, I used it again, non-noble gas, is fluorine. Now, if you notice, hydrogen is on the left, oxygen is on the right. Oxygen is more electronegative. And that means when they're sharing electrons, they don't share it equally. Now, don't tell my sister I'm telling you that, my older sister, I'm telling you this story. When I was little, and she's 7 years older than me, so she was much bigger. I think I was about 5 or 6. We were caught out walking home from somewhere to our house. Now, back then we lived in Chicago, our apartment, in a rainstorm. We had one umbrella, opened it up, and we shared it. But she was bigger than me, and she shared it more over her than me. I didn't get totally wet, but I didn't stay totally dry like her because she was bigger at that time and stronger. I got back to her later on, but that's a story I don't tell. But we're still close. Wow, all these decades. But anyways, this is very important. I'm going to turn the switch on. If we look at water, this is not being equally shared. And I hate to do this, but I think it's a safety thing. Time again for my thumbs up people to see water on the screen. Thank you. Now, another way of writing water is this with lines being a single bond, which organic chemists do. And you don't show the non-bonding electrons. Now, this equal sharing is not equal. And in chemistry, this is delta. This means difference. Capital delta in Greek letter. Now, smaller case delta is this. And this means little difference or slight difference or little. And there's a slight positive charge on oxygen, slight negative charge, positive on hydrogen, negative on oxygen, this hydrogen too. And this is called a dipole moment. Now, if I write another water molecule, and what you don't know is opposites attract in charges. So this negative charge will attract this hydrogen. And see this little dotted line I put in there? There's a very small but very significant attraction. And we call that, even though it's not really a true chemical bond, it still has the name That's better. Hydrogen bond. Look out, it's Subtle Monday. You should know this. Because of the difference in electronegativities, water exists like this, and we have the hydrogen bonding here, which is not a true chemical bond, but a very slight attraction. And why would I put down know this? Now, the answer is following. See my water bottle? Know what's in there? Water. Very good. What physical state is it? Is it a solid? No. Is it a gas? No. It's a liquid. And at room temperature, water is a liquid. If you look at other molecules that have the same molecular weight, you would assume they have the same boiling point or be the same physical state at this temperature. And the answer is no. They're all gases. Water is an exception. Why is it a liquid at room temperature now? Because of hydrogen bonding. The next time you see some water in a glass or open up your sink and turn on the water, it's a liquid because that tiny little force between the water molecules, and that's hydrogen bonding. Think about life on our planet. If water wasn't a liquid at this temperature, we would not exist the way we are today. Think about it, in your blood in your veins. You see my veins? But anyways, here, this is easier. You see my veins? The blood in there is a liquid. If we didn't have hydrogen bonding, it would be a gas, and we sure wouldn't look the way we do today. And think about how life formed, if you believe scientists, coming from our oceans. And our oceans wouldn't be oceans of water as liquid. They'd be like on Jupiter, just clouds of gas. And think about it. Hydrogen bonding has made a big difference. That tiny little force between two water molecules is quite significant. We'll learn more about it. Now, it turns out, what are other atoms or atoms that can hydrogen bond? And those other atoms are, besides oxygen, nitrogen, and fluorine. Ammonia, even though it's a gas at room temperature, can do some hydrogen bonding. And so these are the three molecules that can hydrogen bond. The only one here, HF. Example here, ammonia. And example here, obviously water. Now, I won't teach it in my class, but in amino acids, there's a nitrogen that can hydrogen bond, and that helps form the structure of your RNA and DNA. RNA and DNA, yep. Guess what? That's affected by hydrogen bonding. I talked about bond polarity, how there's a charge there. And polar covalent is what they call a hydrogen bond, but I won't ask that. I talked about slightly negative, slightly positive. And I talked about my sister, two people sharing an umbrella. I talked about water is technically a polar molecule, but I won't talk about that. Key thing is you should know hydrogen bonding. All right, guess what? We have finished chapter 10. Tomorrow, I will go through chapter 9, part 1 and 2, practice problem answers. And one of you politely pointed out chapter 9, part 2 and chapter 10, part 2 are the same. I make mistakes once in a while. Now, On Wednesday, I'll go through chapter 10. If you haven't guessed by now, I'm speeding things up. And that's just the way I always teach chemistry, summer or fall. Hey, keep up. I'll also post later today, like I said earlier, what videos from my 1105 will help you what we're doing now. So what does that mean? It's new chapter time. And this chapter is called Chemical Compositions. Finally, we're going to get into some juicy stuff. Let me just check once more with my thumbs up, people. Everybody see chemical? Thank you. All right. Now, I would have ordered it differently, but the book talks now, and we can bring it in now, something called atomic mass and formula mass. And atomic mass is really atomic weight, and formula mass I call molecular weight. And switches off right now. Atomic mass unit of an element was defined as 1/12 the mass of carbon-12 isotope, which means it's got 12 AMU, atomic mass units, atomic weight of 12. Now, it turns out there are different isotopes of carbon, and therefore you do a percent mass or weight average, and carbon has not exactly a 12 atomic weight. It's a little higher. And mass of an element, which I also call the weight, is its atomic weight on the periodic table. Let's go to periodic table and take a look. Hold on. And if you look at carbon, you'll see underneath 12.011. And I'm going to check once time. Thumbs up, people, see it? Excellent, thank you. I really appreciate your help. All right, now, nitrogen, 14.007, oxygen, 15.999, hydrogen, 1.008. And this is the average of all isotopes of hydrogen, oxygen, nitrogen, carbon to get those atomic weights or masses, AMU. Now, here's my gift to you. It's a tiny gift, but it's make your life a lot easier. On my test and the final, you should only use atomic weights to 3 significant figures. On my test and final, when you're calculating things, you should only use atomic weights to 3 significant figures. Let's take a look at that. You all know how to round off. So for oxygen, you should use 16.0, rounding off 15.999 to 3 significant figures to 16.0. For carbon, it will be 12.0, oxygen 14.0, and let's round hydrogen off to 3 significant figures. I'll let you try that first. It's 1.008, round that off to 3 significant figures. And the answer is 1.01. And instead of using these numbers here, you round it off. Let's do one more. Sodium you should use is 23.0, and chlorine over here, 35.453, you should use 35.5. And this will make your life easier. So an atom has a weight, atomic weight, based on the number underneath its symbol in the periodic table. And all my tests, you'll get the green periodic table I just showed you. You can download it. Oh my God, I've been having so much fun. It's time for a break. Let's take a break, come back at 10 o'clock. Time flies when you're having fun with chemistry. And I'll see you in 5 minutes because I'm going to go do my stretching exercises. I've been sitting for all this time. I've used this in a while. Time to start. Yes, in a classroom, I can get pretty crazy too, but I don't bring the sound effects. Now, here I have formula mass. Another way of saying it, which I normally do, is atomic weight. And for a compound, switches on now, real high. For a compound, you should know that the sum of atomic weights or masses of all atoms is the atomic weight of a compound. And let's do some practice. And let me now, the molecular weight, which I always abbreviate MW, is the sum of all atomic weights. So if we look at water, what is the molecular weight of water? And on tests, I'd write out molecular weight. So how do you do that? In important information, I'll give you this, and therefore, the molecular weight of water is the sum of the atomic weights of all atoms in the molecule. Water has 2 hydrogens, 1 oxygen. Now, what's the atomic weight of hydrogen? Well, if we look at our periodic table, rounded off to 3 significant figures, hydrogen is 1.01, oxygen to 3 significant figures, 16.0. So each hydrogen is 1.01. That's the atomic weight of hydrogen. There are 2 of them. Each oxygen, 16.0. Do the math. Add it up. And you get this. Now, when you do addition, you get the same number of significant figures past the decimal point as the number that has the fewest. All zeros after decimal are significant. This has 2, this has 1, therefore this should have 1. Keep this, use that to round off. It's 4 or less. So the molecular weight of water is 18.0. And later on, you'll know this in one system is 18.0 grams. And why don't you try one yourself? What's the molecular weight of ammonia? Ammonia has 1 nitrogen, 3 hydrogens. If you look on the periodic table, the 3 significant figures, ammonia is 14.0, hydrogen, as I mentioned earlier, is 1.01. Why don't you just try setting it up? And if you don't have your calculator, maybe you can do the addition in your head. Give you 3.4 seconds more. 1, 2, 3, 3.1, 3.2. Time's up. All right, let's take a look at this. You have 3 hydrogens, and you could have started with nitrogen. I like to do it this way. Either way is correct. Each one of the hydrogens has atomic weight of 101. Nitrogen, one of them, is 14.0. Do the math. Add them up, because the molecular weight is the sum of all atomic weights. You get this. This has 2 significant figures past the decimal. This has 1. When you add up, you get the same number of significant figures past the decimal as the number that has the fewest, 1. Therefore, we keep this. This is the round off. That's 4 or less. We'll drop it. So the correct answer, what's the molecular weight of ammonia? And the answer is 17.0. Oh, let's do one more. An important compound that's used a lot in the United States in chemical industry is sodium hydroxide. And sodium has this atomic weight, oxygen has this one, hydrogen has this one. I'll add this up myself because I've already given you, but you have to know the molecular weight of a compound is the sum of all atomic weights, and this is 40.01. 1 significant figure past the decimal, 1, 2, what's the lowest number? Hopefully all picked 1. Keep the 0. This is what you use to round off. It's less than 4, therefore or less, therefore eventually I'll get better writing on a tablet. That looks nicer. And therefore, what's the molecular weight of sodium hydroxide? By the way, this one I know by heart because I use this number a lot, but that's how you find it out. A molecular weight, sum of all atomic weights you should know. And this is how you calculate it. And for sodium hydroxide, the answer is 40.0 using proper significant figures. And notice my gift, using all atomic weights, the 3 significant figures, makes your life a lot easier. By the way, I should point out, when I do important calculations, I use the rounding off atomic weights, and it works quite well. I've done calculations, I'll teach you later on, using that if those calculations, the stuff that would be done in a plant based on those that I've calculated, you're dealing with like $250,000 in chemicals, and you don't want to be wrong when you're messing with that amount of money. You don't mess with it, you get it right. So we've done our practice time. Finally, it's time to talk about some really juicy chemistry, and that's the mole. Now, can I have everybody's attention? Everybody, take a deep breath, let it out. Take a deep breath, let it out. Do you feel nice and relaxed? We're going to be doing some math and algebra. Take a deep breath, let it out. Take a deep breath, let it out. We'll be doing some algebra. Relax, but I'll teach you how to do it. And let's get back to chemistry. Remember, the math we'll be doing, I'll teach you how to do it in case you forgot, and it's not that bad. Now, switch is totally on. The mole. You should know that the mole is the chemist's counting unit. If you go to a supermarket or a donut place, they'll ask, give me a dozen donuts. And everybody knows a dozen donuts is 12. Well, the mole is the unit instead of a dozen chemists use to count. By the way, in chemistry, a mole is our counting unit. It's not that furry little animal that runs along the ground and digs holes in the ground. That's not chemistry. That's another course. But a mole is the chemist's counting unit. And of all the non-organic things in chemistry or basic concepts, the concept of the mole is probably the most important in my mind. Now, a mole, one definition is 6.02 times 10 to the 23rd, whatever. And this is called Avogadro's number in honor of an Italian scientist. Back then, I don't think they called them chemists. Maybe I'm wrong, but 1700s or maybe earlier, that came up with a concept dealing with the mole and helped it. The actual concept of the mole in 6.02 times 10 to the 23rd was really discovered by two Germans, but the key work Avogadro did, they named this after him. Now, if you notice, 6.02 times 10 to the 23rd is a big number. Time to learn something personal about Dr. White. You know what my all-time favorite gift would be for my birthday? And it's coming up in December, so you have time to save for it. And that would be, I would want for my birthday only a mole of pennies. 1 mole of pennies. It's just pennies, 6.02 times 10 to the 23rd pennies. If you were to write a check to that, or think about it, you would need 100 million piles of pennies, and each penny, each pile would be $1 billion. So that'd be 100 million times a billion. That's probably all the money that ever was, ever is, and might be on this planet. But it's just 1 mole of pennies. Mole, large number. Remember, my birthday's coming up. I'd like a mole of pennies. Now, one of the things I'm going to be teaching is some math. When you have one thing equals another in a definition, 1 mole equals 6.02 times 10 to the 23rd, Avogadro's number of things, you can make 2 ratios. These are not equal, these are separate ratios. One is 6.02 times 10 to the 23rd per 1 mole divided by 1 mole, or 1 mole per 6.02 times 10 to the 23rd things. And I'll be explaining why this is important today or tomorrow. This I'm going to skip about moles of elements. All right, let me check something out. All right, I'm missing a slide here. Time for me to go to my whiteboard. And I'll change this, but everybody see my whiteboard with the little pens there? Thank you. I'll have to add this slide. Somehow it got deleted. Come on, pen, pick up. The slide that disappeared from my lecture, and I'll get it in later today. Change that. So it's here. 1 mole equals 6.02 times 10 to the 23rd atoms. And also 1 mole equals 6.02 times 10 to the 23rd molecules. And this is of an element of a compound. Remember, an element is atoms. A compound is made up of molecules. And on a test, in important information, I'll give you these two numbers, just like this. I used to make students memorize this. I don't. Maybe even 5 points even. And the question is, how many molecules are in 5.34 moles of water? So what are we being asked to find? We're asked to find how many molecules of water. What are we given? We're given this number, how many moles of water. And now it's time for me to teach you one of the best things I ever learned for general chemistry. And thank God to Mr. Salmers, I still remember his name, my AP chemistry teacher in high school. And he taught us, really drilled into us, what's called unit analysis. It's got other newer names like, I can't even think of it right now, but listen carefully. Unit analysis is your good buddy, will be, and your good friend. Unit analysis has been Dr. White's good buddy and good friend for a long time. And by the way, at this point, let me warn you, I will be going for the Guinness Book of World Records for the most times I can say, your good buddy, your good friend in a chemistry class. Lots, because it is. Let's look how to use your good buddy, your good friend. Now, what number do we have to start with? Only that number. what answer do we want what units do we want our answer in? This. Now, here's how unit analysis, your good buddy, your good friend works. If I had a magic ratio that I could convert this number in this units to this units, what would that be? Well, you look at what are you trying to get at unit-wise, and you put that on top. You look at what units don't you want? Moles of water. I don't want that in mine. Now, let me remind you, anything divided by itself equals the number 1. So moles of water divided by moles of water cancel out. What units am I left with? Molecules of water. Where do I get this answer? Where do I get a relationship between moles of water and molecules? And the answer is 1 mole of a compound equals Avogadro's number. Now, the other thing I want to remind you, if I have D equal E, I have 2 ratios, D divided by E and E divided by D. And remember, 1 mole compound equals Avogadro's number. I should point out, Avogadro's number is calculated. I use 6.02, most chemists do, which is 3 significant figures. One time I found a website, a reputable one, where they have Avogadro's number to 18 significant figures. I have no idea why somebody would need that, but someone calculated it. So therefore, based on this, I know for every 1 mole, I have 6.02 times 10 to the 23rd molecules. And now, before I pick up my calculator, I'll notice moles divided by moles cancel out. Anything divided by itself is the number 1. The only units I'm left with is molecules of water, and I'm on the right track. And now, hang on. I take 5.34 times Avogadro's number, 6.02 times 10 to the 23rd. This is what my calculator gives me. Remember, 5.34, 3 significant figures. Avogadro's number, 3 significant figures. I round this off to 3.21. Keep the 3, keep 2, keep the 1, use the 4 to round off. It's 4 or less. So the answer is 3.14. Let's see if I copy that number right. Nope, I didn't. I was thinking it's the wrong thing. And that's how you do it. Let's go through how you use unit analysis. When you have a word problem, relax, take a deep breath. The first thing you do is find out, what are you being asked to find? How many molecules of water? What are you given? 3.34 moles of water. Unit analysis. If you can convert one thing to another by using a ratio, you look at, what do you have to start with? This, and the units is important. Next, what are you trying to get to? Write down the units. And here's where you use your good buddy, your good friend. Whatever you're trying to get to, you put on top of a ratio. Whatever you're trying to get rid of, you put underneath the ratio. And where do you get the relationship between 1 mole and molecules of a compound? 1 mole of a compound equals Avogadro's number. I didn't write it down, I should have. Of molecules. And now 1 mole goes here on top, Avogadro's number. Notice moles divided by moles of water cancel out, because anything divided by itself equals the number 1. Therefore, moles divided by moles is the number 1. It's gone. And therefore, we're left with just the only units what we want, and that's molecules. This is 3 significant figures. 3, our answer, we rounded off to 3 significant figures. And that's how you use your good buddy, your good friend, unit analysis. Again, the key thing to remember, 1 mole of an element equals Avogadro's number in atoms. Avogadro's number, 6.02 times 10 to the 23rd. 1 mole of a compound equals Avogadro's number in molecules, and that's 6.02. And I really should change this to know how to use this. I will give you these numbers right here in important information for test number 2. In the past, about 2 years ago, I used to have students have to memorize this. Then about 2 years ago, give or take a semester, I came up with the thought that, am I grading students by how well they memorize it, or should I be testing how well they understand chemistry? I came to the realization for general chemistry, it's how well you understand chemistry. So good news, I no longer ask you to memorize those, I'll give them to you, but you do have to know how to use them, and you do have to know how to use your good buddy, your good friend, unit analysis, which makes your life so much easier. It has mine for many decades. I've used unit analysis to make calculations where $500,000 are riding on do it right, and I did. With that, I think we're out of time. With that, I better use this because I haven't, well, I did once, but I'll do it again. Time's up. Hopefully you had a fun day, morning with Dr. White. Gay and gesund, be healthy. I'll see you tomorrow. Don't forget to download the lab that you'll do tomorrow. Don't forget by tomorrow, go into Labster for last week's lab and just try it a little. If you're having trouble with Labster, let me know. And I think one of you had questions about Labster. I'll stick around for a couple minutes now if you have. That one person is here. And also, don't forget my office hours. Bye.